So today we'll be going over the method of joints, and this method is utilized when analyzing truss structures. And so, first off, what exactly is a truss? A truss is nothing more than slender members connected at their joints. In this case, at their each of their ends, you have a slender member connecting to one another, and this is what's known as a truss. These are very commonly used in bridges and so forth, and so this is a common structure that we see, which are trusses. And in this video, we'll be going over how to analyze a truss with, let's say, an external force being applied, and to be able to solve for the forces that each of these members will experience caused by those external forces on that structure itself. So let's go ahead and do an example of that. Now, one thing to note that at each of their ends, they will be assumed to be pinned connected. Although there are other methods, the way these members are joined, we will be assuming that they're pinned connected. So this problem statement says determine the force on each member of the truss and state if the members are in tension or compression. And we have two forces being applied at point B. We have a 100-pound force being horizontal, and we have a vertical force at 500 pounds being applied to point B. So one thing to note are the supports of this structure. Of course, this is a truss. We have slender members. In this case, they're either rods or they're beams. And so one thing to note are the supports. We have at point A, we have a hinge, and at point C, it's a little bit it's a different support. We have what's called a rocker here. So this is where you would refer to the appropriate reactionary forces, what directions you would be expecting these. So the first step is to basically get your reactionary forces. In this case, a reaction force for a rocker is vertical, so we're going to say FC on the Y direction. And for the hinge, we have both a vertical and a horizontal here, so F A Y and F A X. So the first step, we first, based off the external forces being applied on the structure itself, on this truss, we go ahead and solve for the reactionary forces first. So, of course, for static equilibrium, we have the sum of moments I'm choosing with respect to A are equals 0. So let's go ahead and do that. So now that we solved the static equilibrium equations, in this case the summation of moments about point A equals 0, summation of forces of x equals 0, summation of forces of y equals 0, now we were able to solve the reactionary forces at A and C. We get f of c of y is equal to 71.43, f of ax equal to 100 pounds, f of ay is equal to 228.57. Now, this is where we start doing the method of joints. So, since these members are connected at joint A, B, and C, we essentially choose a joint to analyze and only analyze at that specific point. Now, when you're considering choosing a starting point to analyze, it's always best to choose a joint that only will have two unknowns for so two unknowns, so not to have more than two. So let's go ahead and analyze joint B. So doing a free body diagram of that joint specifically, we have the external forces of 500-pound and 100-pound being applied at point B. But one thing to consider are the forces being produced within the members themselves, basically reacting to those external forces. So one thing is we could assume the forces within those members, let's say members B and C. I will go ahead and assume the force within that member being FBC here, and I will also assume this force within that member FBA. Now, depending of the direction of this forces, that member will either be in tension or being stretched or being compressed or squeezed, right? In this case, since I will be from the joint to this direction, essentially this is how you would draw or represent tension, and compression will just be the other way around. That would be the reaction of that member. But right now, I'm assuming that the members are in tension. You use your static equilibrium equations. In this case, since we're applying it only to a specific joint, the summation of moments won't really be useful in this case, but the summation forces along the x and y direction will be. So let's go ahead and do that. One thing I did forget here, you would also need to know the angle, but since we have the necessary dimensions or the rise and the run for these members here, we have a rise of 8 feet as well as 8 feet here. This one, since we have the dimensions given to us, this one's 6 and this one's 8, and we could go ahead and solve for the magnitude there, the hypotenuse of that triangle. So for the sum of forces along the y direction, I'm choosing my sign convention up being positive. So along the vertical, we have negative 500 pounds going down, plus F of BA times, we're using the sine theta, so it's opposite over hypotenuse 8 over 10, plus F of BC, opposite over hypotenuse 8 divided by square root of 128, and this is equal to 0. Now let's do the sum of forces along the x direction. So we have for the summation of forces along the x, negative 100 pounds since it's going to the left. Take away FBA times adjacent over hypotenuse 6 over 10 plus F of BC since it's going to the right. It's a positive sign convention. FBC times adjacent over hypotenuse 8 divided by square root 128. And this is equal to 0 for static equilibrium. Now we have two equations and two unknowns. The unknowns here are the members, the forces along those members of BA and BC. So what we do here is we use either or equation and solve for one variable. So let's say I'm going to solve for f of BA here. Let's solve for that. So we just move some stuff to the other side, then multiply by 10, divide by 8 to this. We could actually simplify a little bit further. And we have f of BA is equal to 625 take away FBC times 10 divided by rad 128. So now since we have FBA here, let's go ahead and plug this equation into here. Let's go ahead and do that. So we have negative 100. Once we plug in f of BA and distribute accordingly to the 610, so we have take away 375 plus FBC 6 divided by rad 128 plus FBC times 8 divided by rad 128 is equal to 0. So one thing you'll notice here, we basically started with two equations, two unknowns. We solved for one unknown with having the other unknown within that equation, right? Then we went ahead and plugged it into the other equation that we have, such that we're able to only have one variable in this one equation, so that we're able to solve for that unknown variable, in this case f of BC. So now after you do some simplifications, you add, you change some stuff around, you finally solve for f of BC, which basically gives you 383.86 pounds of force in the member BC. And remember, this is in tension, so let me just put a T. It's basically being stretched in this case. Now, since we have f of BC and we have an equation for f of BA, we just plug in f of BC in this equation and solve for f of BA, which gives us f of BA is 285.71 pounds. And so this is the method of joints. When it comes to the other force member AC, you just repeat it. You repeat the same method for either joint A or joint C to give you the force in the member AC. So now looking back at joint C, we have two members, F of BC here, which we found out to be 383.86 pounds being in tension, so basically pulling away from that joint. F of AC, we're assuming its intention. So one thing I did forget to mention is if our answers F of BC or BA were negative, that just means our assumptions were wrong. Instead of it being in tension, it would actually be in compression, and that's what it would mean when it comes to the sign convention. So F of AC, I'm assuming it's in tension, so we're pulling away from that joint. And we have the reactionary force at point C, which was 271.43 pounds. So again, we do the equation of static equilibrium. In this case, since we have no vertical force for F of AC, we're only going to deal with the horizontal forces. So we're going to do the sum of forces along the x direction. So negative F of AC, take away 383.86 pounds times 8 divided by rad 128, because we're only looking at the x component, and since the x direction, this member force is going to the left, which is opposite of our sign convention, so it's negative. This equals to 0, so we get F of AC is equal to, we end up getting negative 271.43 pounds. Now remember, the sign convention just means if we get a negative, it means our assumption was incorrect. Since we did assume it was in tension, that means with a negative, it's actually not in tension, but in compression. And this is how you would draw to represent a member in compression. So FAC is equal to 271.43 pounds, and this member is being compressed. It's in compression. And so this is the method of joints where you go ahead, you do your free body diagram, but you go at the joints. You look at the forces of those members being produced or reacting against the external forces being applied to that structure. And so right now I'd like to take some time to explain a little bit about the members in tension and compression. So let's go ahead and just assume any any joint. It doesn't have to be related to this specific problem or whatever. But let's say we have two um, slender members here at this joint. Let's just say this one, we have this force F of AB, just arbitrarily choosing the letters, and this one is here, F of AC or whatever. Now, this member here essentially is being compressed. This is how you represent being compressed. The member is basically getting into the joint. This is how you would signify compression, whereas in tension, you'll be pulling away from the joint. So let me go ahead and draw a slender member just to explain this a little bit more. So let's say we have this slender member joined at the pin at this hinge here, and we have an external force being applied, vertical, downward, whatever this force may be. Now let's go ahead and look specifically at this joint. Now, just by observation, we could see that this slender member is going to be stretched. So in other words, this member is in tension, right? It's being stretched, and so it's in tension. Now let's looking at specifically the joint, the reactionary force is going to be equal and opposite at this, right? It's going to be upwards because it's resisting that external force. That hinge has to be um, acting equal and opposite to hold up that member. And so whenever you just draw the member here, we have the member, the force within that member itself is being pulled down. So this is the action of the member being pulled downward at this joint, and of course the hinge itself has to react equal and opposite of that for force equilibrium. Now let's say let's say that this member was being compressed instead. In this case, you would draw that joint, and since this force would be essentially upward here, the reaction force would have to be downward. So looking at the slender member here, it would basically, you would have a force going towards that joint because it's being compressed, and the reaction of that hinge is equal and opposite. So this is where that convention comes from, the way you draw your members in compression and your members in tension, right? One of them is pulling away from the joint while the other is basically pushing at the joint. And that's essentially the way we represent members in tension or compression.